stuff or more stuff that's pre-written. But generally, if you like, you can download the template and fill it in as you go. Otherwise, just watch the lecture, and at the end of each lecture, I'll post the PDFs that we write on here. So today, it's always going through all of the housekeeping stuff. I'm always meant to say where the exits are. You can see where they are. But everything's on the Canvas page. You're probably already familiar with that, so it's kind of pretty uniform now across different courses. In that Canvas page, well, the Canvas pages don't all look different across different courses, but there's a unit outline. Homepage gives links to some online text. You don't need any textbook for this, strictly speaking, but there's thousands of good linear algebra textbooks out there, free ones. I mean, I wouldn't recommend going out necessarily paying for anything. The homepage gives some books you might want to look at. It's always good the more you look at, the better, getting more perspectives. And in fact, the act of just simply finding books and going through them, trying to identify the words that match up with what we're doing is already, I mean, that step alone is helpful revision. In particular, though, the unit resources gives all our tutorial sheets and all that kind of stuff. Okay, I'll go kind of quickly through this. So there's as you know already, there's the lecture that you're already here for. 1 o'clock we'll finish, so we'll have a little break at midday rather than having 2 hours straight. There's a 1-hour lecture on Tuesday. All the lectures are live. I highly recommend actually coming, but they are also recorded and the PDFs are posted if you miss them. Let me know if you've got any questions as we go. The seminar, that's maybe a bit different than things you've done in first year. So that's like a practice class. It'll be with me in, well, this room or some similar room. I've forgotten where it is exactly. That's on Thursday at 11 a.m. And that's the time, well, first of all, you can ask questions, but there's also going to be a pre-prepared sheet, practice class sheet with lots and lots of questions that you can work on. But we'll sort of highlight some and work through them perhaps together a little bit and get questions as well. Okay, so they're sort of on top of tutorials. It's a bit of a different process to tutorials. There's also a quiz in week 9, an in-person one that's actually held in that seminar class, okay, that Thursday seminar. So of course that's one place you can't use AI and all that stuff. There'll be a consultation starting from next week, week 2 to 13. That's Thursday at 1 p.m. But just feel probably easiest, use the Ed forum, which is coming up later. Write questions in Ed. There's me and 2 other tutors, and people will be looking at that Ed discussion forum. You can also write emails if you have any questions, or ask me after class. I mean, there's plenty of other opportunities. Tutorials, indeed, they'll be sort of in that style like in first year ones, where you get up on the blackboard in small groups, working in small groups yourself. Hopefully everyone's okay with that. If not, that's, you know, it's an opportunity to work yourself as well. Check your timetable when it is. I have no control over the timetable, so if it says blocked and all that kind of stuff, you can't go to this tutorial. Just go to a tutorial that suits you, talk to the tutor. Hopefully there'll be enough space. But the central system is a bit of a, well, a bit hard to navigate, I appreciate, and I don't have any control over it. All right, there is a tutorial mark. Only 8 out of 12 count to your mark. So keep that in mind in terms of applying for special considerations and so on. You'll need to have a special consideration that covers, you know, five weeks, and then you'll start getting special considerations, yeah, from that 5th week onwards, okay, in terms of some kind of reweighting onto your exam or something. I don't know. But anyway, so if you miss 1 or 2, it's fine. In fact, if you miss 4, it's fine. I don't advise it, but you won't lose marks. Ed Forum, you already know about that from first year. That's a great place to ask questions. Assessment structure. It's unfortunate this room we only have 1 slide, so I can't freeze. I think the other room we're in might have 2, and we can freeze, but sorry about that. We have to go through kind of fast. Today's faster than normal as well. Okay, so it's pretty standard kind of assessment structure. 60% will be on the final exam. There'll be 2 assignments, week 6 and 12, so spread out through the semester. There'll be this supervised quiz in week 9, so you can really treat that like a midterm exam sort of thing. We'll talk about that as we, at the right time, and have some. I haven't thought about if we have practice questions and stuff, but we'll do that at the right time. Online quizzes, yeah, so they'll start in week 3, just to give us a bit of I don't know, it's not much point having one in week 1 in a way. So the week 3 one is the university's mandated early feedback task thing, and then the other one's weeks 5, 7, 9 and 11. So odd weeks starting in week 3. They're on Canvas and they're quite relatively basic multiple choice questions. They're meant to be just log in, do them. They're not meant to be a super stress. Yeah?
How far ahead of the quiz due dates the lectures typically due that week and then do the quiz?
Yeah, good point. I think it's, let me double check that, but I think, so this is my second year teaching the course, and so last year I was writing a lot of things and getting the content lined up. I should double check that my intention would have been, and I should check I really have stuck to that the quiz in week 3 will be on week 2's material and before, like mainly on the previous weeks or previous 2 weeks material, let's say, because they're every odd week. But maths is cumulative, so it's really everything. So you won't have to have done week 3's lecture, I don't think, to do the quiz, but I will double check. Yeah.
I just wanted to check, because this particular lecture apparently is like unclashable, but it also happens to clash with one of the vector calculus tutorials.
Yeah, it's not very unclashable.
Like there's an exam during this lecture.
There's no exam in this time. No, that's right. Again, that's not something I clicked a specific button to make it unclashable. This is just a regular lecture, and if you have a clash with something else, it's up to you. Can make the choice of which one you go to, with keeping in mind, make sure you catch up the material from the other one. Yeah, so I'm not sure about that. But the vector calculus one is not classed as unclashable.
That's a tutorial. So
Oh, right. Okay. Strange. Anyway, yeah. The mysteries of the central timetabling system, I don't know about. Tutorial participation, as we've discussed. Yeah, so we've already discussed that. Good. Yeah, you should refresh some stuff from Math 1961. We are going to see, we'll do everything again. I will remind you of things when needed, but it's definitely helpful to have a bit of a understanding, of course, because we won't redo everything. So remember, in particular, the language of injective, surjective and bijective functions, that's just crucial for all of mathematics in everything that follows. So make sure you really know what injective means, have a good feeling for it, surjective and bijective. Okay, make sure you do know those. They're things that maybe you hear them the first time and think it's not that important. It is really important. Systems of linear equations, that's what linear algebra is all about, ultimately. So remember what they look like, but we'll refresh that at the right time. Matrices, see, you learned matrix multiplication last semester, or maybe at school even. Make sure you know how to do that. We're definitely not going to go back over matrix multiplication. So make sure you're very comfortable with playing around with matrices. Inverse and determinant, we are going to revisit those concepts, but why not remember them a little bit already? And eigenvalues, eigenvectors, again, we're going to revisit those in a more sophisticated way, I guess, trying to really see what's going on. But it helps if you already have a feeling for how to calculate those things. So they're words you should have already heard before. Vector spaces, in particular, if you did the mainstream course in first year, you may not have talked much about span, linear independence, basis and dimension. If you did the advanced course, you would have. Refresh those concepts, but we will also revisit them, as I've said in the green box. Helps a lot if you know them in advance. All right, so I'm kind of changing things around with this unit, and I didn't, in time, change the weekly schedule that's on the unit outline. The university makes everything happen very early. So in particular, I just want to emphasise that the content's going to differ kind of substantially, actually, from what the weekly schedule says on the outline. And the main difference is that we're doing the linear algebra part first and the group theory part second. I think the mainstream course might be doing it the other way around, so just keep that in mind if you're making decisions on changing streams. There is a logic for that. I mean, group theory is the more abstract algebra, and well, you should do the more concrete linear algebra first. It helps a lot with understanding the group theory. You use linear algebra to study group theory, in fact. So it was a bit strange the way it was done. I can see why it was done the other way, because you can also define groups very abstractly, and then you can state things like vector space axioms in terms of group axioms. So there's this like two ways you can go about it. But I think the first time you learn it, vector spaces and stuff are the concrete things. Group theory is the more abstract stuff. Okay. So it'll be reversed. So because of that, I did make a revised schedule. I'll go through this super quick. But anyway, this is the schedule that roughly we'll stick to. So week 1, which is this week, is going to be fields and vector spaces. Week 2 is span, linear independent spaces and dimensions. So they're things you're familiar with, but we're going to prove things in a, well, hopefully fairly different way, or things that weren't proved initially. And a main difference, so vector spaces need a field of definition, the scalars. Probably last year you focused mainly on the real numbers and the complex numbers, but to begin with, we'll work over arbitrary fields, which is like finite fields and all that kind of stuff. We'll discuss that a bit later today. Basis, all that stuff. Week 3, linear transformations. That's when, just to get the words starting to flow, when you've got 2 vector spaces and you're looking now at maps between them that preserve the vector space structure. So that's vector spaces themselves are somewhat kind of static things, and then linear transformations is when you start moving things around, doing things to the vectors. Okay, that's linear transformations, and then there'll be ideas of images and kernels, as there are, and then also since we'll work abstractly with linear transformations, when you come back to the concrete vector space of Rn or Cn or some other field to the power of n, you can then write out a matrix representation of your linear transformation. Okay, so this may be week 4. Okay, this first one won't make much sense right now. We'll rediscuss just because we sort of need it. You're meant to know all of the row operation and Gaussian elimination stuff, but we'll just say a little bit there just because it's appropriate at that time to remind us of some stuff. But we'll use it already in advance, a bit of row operations and stuff. And we'll talk about something called the rank nullity theorem and its consequences. Week 5 is all about basis and changing bases of 2 different vector spaces. Often in linear algebra, you have some vector space, underlying space that you're working in, and you have some linear operator, and you want to understand that linear operator. And by picking a sensible basis of the underlying vector space, that linear operator takes a particularly nice form, like a diagonal matrix or something like that. So you need to be quite fluent at being able to take a basis of a vector space, change it to another basis, pick a basis that works properly for a linear operator, and all of that. That's what that we'll be talking about. Also, determinants, we'll introduce them properly. I think probably you just had a brief definition last year. And then week 6, coming to stuff that you are already familiar with, but we'll treat things in a much more general way and try to give the full picture. So eigenvalues, eigenvectors, we'll also look at things called generalized eigenspaces, which is what you need to overcome the non-diagonalizability of matrices. And that leads us all the way through down to decomposition theorem and Jordan normal form. So it's weeks 6 and 7, which is kind of like you already know you can't diagonalize every matrix. The thing you can do to every matrix over the complex numbers anyway is put it into something called Jordan form, which is the simplest way you can write the matrix, basically. There'll be some applications of that. We'll come to that later. Week 9, so that first part is all up to vector spaces and up to Jordan form, which could be expressed as understanding vector spaces and linear transformations, because Jordan form is something for a linear transformation, in fact. And then we'll come to a bit more slight change of tack, where we now look at inner product spaces. That's where we have to look at the reals or the complex numbers instead of arbitrary fields, and we start looking at ideas of angles between vectors, and so basically it incorporates a bit of geometry into the vector space. And that just goes for a week, really. That's a bit of an introduction into later courses like metric spaces and functional analysis. And then we'll start the group theory part only in week 10, and that'll be week 10, 11, and 12. And we'll try to get as far as normal subgroups, quotient groups, and the first isomorphism theorem, or fundamental theorem of group homomorphisms. week 13 will just be revision and loose ends as we need. Okay, so there's some words. Maybe they don't mean heap right now. Maybe they'll mean a little bit more later. So now there's a bit of redundancy here, so maybe I'll go quick because I've already gone through the weekly outline. But I just want to say a little bit what linear algebra is actually about. I'll basically just really read this, but first of all, it is essential to most things you'll do in the rest of mathematics. It's very useful, arguably the most useful. People often think calculus is the most useful, but in fact, linear algebra is kind of studying the structure more and pops up everywhere from multivariable calculus, differential equations, all of this stuff here. Higher algebra, Galois theory, if you're planning on doing pure maths next year, that's our best course, no doubt. Physics, economics, data science, statistics, just everywhere you have a lot of data or a lot of structure, linear algebra is going to be there. A bit of warning, it takes some time and effort to master linear algebra. People often think it's pretty abstract at the beginning, but once you get used to it, you'll realize it's actually extremely concrete. That's the point of it, representing linear operators with matrices. These are things you can multiply together, find inverses, find determinants. It's very, very concrete once you understand it. Okay, so it just takes a bit of time, I guess. At the simplest level, I already said this earlier, it's really all about systems of linear equations. And to make it sounds a bit boring when you say it like this, but at its heart, that's really what it's about. It's trying to solve systems of linear equations, which are written in matrix forms like that. Linear algebra provides all kinds of algorithms and efficient techniques to do so. But it does go much further than that, of course, studying the structure of vector spaces, linear operators, and so on and so forth. But why it's so important, and I'm going very quick here, but you can read this later a little bit. Why it's so important is that a lot of situations in physics or applications are governed by linear systems, like linear equations, AX equals B in matrix form. It sounds very restrictive, and indeed it is. Not everything in the universe is a linear system, but an awful lot of things are. And even in the case when you have a nonlinear system, basically the point is in a nonlinear system, that's where you don't have all the algorithms of linear algebra. You don't have ways to solve things. And the standard approach, the first approach you would do is linearize the system at various points, look at lots of linear systems and glue those and solve them using linear algebra and glue them back together to get something that approximates at least a global solution. So kind of a philosophy. So linear algebra is kind of, yes, it's restrictive. It's a linear system, and linear does sound restrictive, and indeed it is. But in that restricted sphere, you can do everything you ever want to do. Like you've got all kinds of very efficient algorithms. You can work very, very well with linear systems. And then you can apply it to nonlinear things as well. We're not going to go into all of that stuff, of course, but it's just trying to say, anyway. And maybe I'll skip through this, because we already talked about all of, well, no, I won't. We went through the unit outline, so I'll the weekly outline, but we'll repeat it a little bit. We're going to study fields today and a little bit tomorrow, but tomorrow will be vector spaces. Fields generalize the reals, complex, and the rational numbers. Once you know what a field is, you can define a vector space that requires a field as its scalars, what its numbers are, and then the vector space has vectors, and the numbers multiply onto the vectors and stuff. And you get linear combinations and all that kind of stuff. Basis and dimension of vector spaces, linear transformations between vector spaces. As I say, this is a fundamental concept. The operator T, these linear transformations, modeling your differential equation or whatever it is in various applications. So these are the things you often want to study. The underlying vector space is somehow this ambient static thing, and the linear operator is the thing you're actually typically trying to solve or understand or something. Matrix representations, change of basis, okay. I have sort of said all of this. We'll talk about Jordan normal form. That's quite a lot of work to get to there, but I think it's worth it. By that stage, you really understand linear transformations from a vector space to itself. These are called endomorphisms. The familiar, common situation where the linear transformation has the same domain and codomain. In this case, Jordan normal form gives you the most sort of precise understanding of that operator that you could hope for, in a sense that it's the simplest you could possibly hope for. Then we'll move on to the inner product spaces. That's when we start getting a bit of geometry on the vector spaces. Unitary and Hermitian matrices. These are going to be certain types of linear transformations that preserve the angles and stuff that we have on our vector spaces. And probably no further topics because time runs out. But we'll see how we go. Group theory. Group theory, what it is definitely it's a very nice part of mathematics. It's in a way the first abstract mathematics you see, sort of. Well, it depends how abstract this sort of abstract approach to linear algebra wants to be considered. But linear algebra, as I say, should be considered concrete. And then group theory is when you start trying to abstract things a little bit more. And it's really the study of symmetry, but trying to, instead of looking at the object, trying to look at it, you look at the set of symmetries the object has, and you actually throw the object away and just study its set of symmetries, and that now can be the set of symmetries of all kinds of different objects. So you sort of understand things more intrinsically just by their symmetry. So it's kind of the foundation of abstract algebra in some sense. In a certain way, it's a group, so it's an abstract, it's an object, a mathematical object called a group. In some ways, it's the simplest in that its axioms, the things that you need to define it, are small as possible, essentially, to get a nice kind of structure. But in some ways, that makes it the hardest, that lots of different things are groups, because lots of different things satisfy these very few axioms. Once you get a huge long list of axioms, like we'll see for vector spaces, well, it's very rigid, and only things that are called vector spaces satisfy them, and they're very easy to understand in some sense. But groups are harder in the sense that there's a wide variety, like a big zoo of examples of groups. Anyway, we'll look at lots of examples, of course, and try to understand it. It's a great part of mathematics. So we'll look at definitions, basic properties, and some stuff. We'll get there. There's a lot more you can say, and we'll work that out as we go. In terms of where you go next, things that directly build on this. In third year, there's the rings, fields, and Galois theory. So I'm not sure, is there a specific group theory course starting this year? Or it might be next year. I wasn't sure if it got through the system yet. So anyway. Okay, so rings, fields, and Galois theory is abstract algebra in third year. That's our sort of flagship algebra course, I would say. Metric spaces is a bit of a link between algebra and analysis, as is functional analysis. They're kind of quite closely linked. That's an honours course. Representation theory certainly uses everything we discuss in this course about vector spaces and linear operators. That's one of the specialties of the research department here, in fact, representation theory. So that's an honours course, and also commutative algebra in honours. Anyway, so that was a lot of just talking, but I hope it helps to sort of see where we're at. Are there any questions? Yeah.
Are we doing subspaces?
Yeah, so when we talk about vector spaces, we'll already talk a lot about subspaces. And that'll be an important concept, in fact. When we have a linear operator between vector spaces, we'll often look for what are called invariant subspaces, and that'll let us break down the linear operator into smaller pieces. So, yeah, definitely. All right, so let's start some content. I'll just get to my right place. So first of all, so we're going to talk about fields and vector spaces this week. In linear algebra, fields are probably the most basic concept in the sense that you need a field to start talking about a vector space. And you should be thinking of them. So vector space for now, just do think of Rn or whatever, like, tuples of real numbers, and you add them together, and you can multiply by a scalar, and those scalars are the real numbers. Okay, so the field is going to be the set of scalars, the thing that rescale the vectors, so to speak. But in fact, there's a lot of theory that you can talk about just in terms of fields. They're extremely beautiful things. You can study fields in their own right. And just as an example, something called algebraic number theory is studying field extensions of the rational numbers, like algebraic field extensions. There's a whole lot of number theory involved in understanding fields themselves. So just a warning, I remember when I first learned fields, I thought there was not many examples, and it was kind of a, not a big zoo of examples, but that couldn't be further from the case. We'll try to see some examples, but you'll study fields rigorously in 3962, the Galois theory course. Okay, so today we're just seeing definition, some examples. And our favourite examples are the rationals, reals, and complex numbers. So anyway, so I know we're going kind of quick today. And this slide, well, it's going to be 2 slides, unfortunately. It's relatively overwhelming, but the point is here, so in linear algebra, even though it's not called abstract algebra, we're trying to take an abstract point of view. We have to say what a vector space is, and we do that by giving what are called the axioms for a vector space. So these are the things that the vector space has to be something. Well, and this is what it is. Field. A field is a set F, and it's got to have some operations. So that's a plus and a multiplication. And it's got to satisfy a whole heap of properties. And the idea with axioms is it's not sort of completely set in stone what that set of axioms are in a certain sense. But you want to make a relatively small list of things from which all the properties you want of a field follow from that small list of axioms. So for example, in the real numbers, what we can do is multiply things together, we can add things together. It doesn't matter which order you add things in, it doesn't matter which order you multiply things in. We can also expand out something like A times brackets B plus C. So we know how that's telling us how multiplication and addition interact with one another. When you have a non-zero real number, there's an inverse, there's a 1 over that number. When you have a real number, there's a negative as well. And basically that's it. Those properties, there's also a 0. You sort of need that to talk about additive inverses, and there's a 1. But those properties are essentially the axioms of a field. All of those, any set with 2 operations that satisfy what I just said is going to be called a field. Okay. And then from that set of axioms, we'll prove some basic properties. Right. As I say, though, it's not completely, this is one set of axioms that work. It is possible, if you look in other sources, that they've taken out one of the axioms and replaced it perhaps by something else, which ultimately is equivalent. So the point is it's not completely set in stone. But let me try to explain these things. These are things, in a way you have to remember them, but in a way they're not hard to remember. You certainly don't have to remember the numbering I have here. That's completely arbitrary. F1 to F9, I think I've got. That's completely arbitrary. But you have to know what each of these axioms mean. So let's break them down first. These ones here are saying, I didn't say this one in words, this is an easy one to forget. This one is saying that the grouping of terms doesn't matter. Okay, these 2 axioms. So with both the addition and the multiplication, let me step back one step. To say that you've got operations, that means if lambda and mu are in our field, then these operations are defined and stay in the field. That's kind of hidden in the definition. Okay, that's kind of a little bit hidden there, just to be clear though. So these first 2 axioms, does anyone know what they're called? Yeah, good, associativity. Of both operations. These ones here are good, commutativity of both additions, both operations. So the first 2 are saying doesn't matter how you group things. Next 2 are saying doesn't matter which order you do the 2 things in. The next 2 are really building up to the idea of negatives, which are called additive inverses, but negatives, and multiplicative inverses. But to talk about those, you need to have a 0 and a 1. So this one is existence of 0. Okay, so there exists initially in the axiom just at least one thing that we're going to call 0. It's not the 0 the 0 of the real numbers. It's some element of the field that I'm going to give the symbol 0 to. And that symbol has to have the property that when I add it on to anything, I don't change that thing. I mean, that's what 0 is meant to do. And a priori at this stage is just saying there exists at least one of those things. It could be 100 million different zeros, but we'll see later there isn't. There can only be one. But that's not an axiom. That's okay. The next one is existence of an identity. And there's a little, we sort of want the set that just consists of 0, with 0 plus 0 being defined as 0 and 0 times 0 being 0. That guy, we don't want to call that a field for various reasons. And if I took away the 1 not equal to 0 condition, that sort of silly case of just 0 would be called a field. But anyway, so it's sort of hit that part tears that example out, just because things often don't hold for that. We want to get rid of that. So this is the anyway, but this is a 1 multiplicative guy that when you multiply it onto anything, you don't change that thing. So it's the existence of a 1. And then the next two axioms are about negatives and inverses. So whenever I have, like in the field of real numbers, 7, I have minus 7 as well. And that's a property that's an element with the property that when I add minus 7 onto 7, I get 0. Okay? So just notice at this stage, though, in a field, there's sort of technically no such thing as subtracting one thing from another. What it really means to do 7 minus 7 or something is 7 plus the additive inverse of 7. 7 plus minus 7. Okay, but at a certain point we relax a bit more when we're working with fields, but at the beginning it's important to really crystallize what is going on. It's just a set with two operations, and whenever you see a minus sign, it means this. Again, in this axiom, there could be 53 different additive inverses of 7. It'll turn out there isn't. There's going to be a unique one, but that's not part of the axioms. That's something we'll prove from the axioms later. All right, and this one is the existence of inverses. Here, of course, we need lambda to not be 0. There's no number which, when you multiply it onto 0, gives 1. Just in our favourite examples of R and C and stuff. So we keep that here. And then finally, an axiom which people sometimes forget. I did say this one in words earlier. This one is where you've got two operations, and this is the one that says that they're compatible somehow. All of the other axioms only involve one of the two operations. This one involves both. And what's this one called? Yeah, good. Distributive law. Okay. And of course, there is a distributive law when the lambda is on the other side, but we don't really need it because we know multiplication's commutative, so we can move the lambda across to the other side and do it like that. Okay, so as I say, you sort of need to remember them, but I wouldn't remember them as a list of F1 to F9. I'd remember what they're saying. It's sort of unlikely I'm going to say just write out all the axioms, but anyway. In terms of notation, we often forget the dot notation. It was just there for clarity, really, in the definition. So the dot is often written as just juxtaposing lambda and mu next to each other, or sometimes with a x multiplication sign like that, the little cross thing. They're not new operations. They're just the same thing. It's just for convenience. As I said, the numbering is completely arbitrary, F1 to F9. So in a proof or something, we'll see some examples in a bit where you prove something using the axioms. Don't write by F9, by F7 or something. When you write, say, by associativity of addition, by commutativity of multiplication, by distributivity or something like that. That's the better way of explaining when you're going from one step to another using axioms. But we'll do that in a minute. But first, some examples. As I'm sorry, we have to move quick because we don't have the ability to freeze the screen. That's unfortunate. Familiar examples are rationals, reals, and complexes. And you don't have to sit and write out the axioms for the proof of all those axioms. It's super, super clear. So to emphasize again, the axioms are meant to be something that we fight with to try to check the axioms or whatever. They're meant to be a convenient little list of things that as soon as we know any object satisfies that little list, then they're going to behave in a nice way like a field, the thing that we want to call a field. Okay, it's clear that all the axioms hold. Sometimes you do have to fight a little bit more to check some axioms. So let's look at the next example, or non-example as it may be sometimes. So Zn with operations mod n. I'm assuming everyone's seen that, so you take the remainder on division by n. Okay, but let's just do it. So everyone has seen Zn, correct? Yeah. But let's just do an example. So in Z5, what's 2 plus 4 in Z5? Yeah, it's 1. I don't know if that helps much to write it like that. The 5 is 0 is the point in Z5. What's 3 times 4? 2 indeed. And what's 3 inverse? 2, good. So that one I will explain. That's because 3 times 2 equals 6, which equals 1 in Z5. Okay, so to find the inverse, I don't do, it's not 1/3. Like it's not 1/3. You can't talk about 1/3. Well, it's not that wise to try to think about 1/3 in Z5. Z5 just consists of 0, 1, 2, 3, 4. That's what it consists of. And the inverse of 3 should be one of those things, 0, 1, 2, 3, 4. And if we're worried which one it is, we can just start multiplying 3 by 0. Well, that's 0. 3 by 1 is 3. That's not 1. 3 by 2 is 6, which is 1. So you can just go through the list. There are more efficient ways, as you'll see in tutorials and so on. But you can just go through the list. We will come back to that, actually, when we're talking about group theory later on. Okay, so that's all okay. So what's the inverse of 4 in Z5? It's again 4, because 4 times 4 is 16, which is 1. Okay. I'll just add that one in there as well. No one's shocked by any of that? Everyone's happy? We'll definitely do calculations in ZP quite a lot when P's prime, or Zn more generally. As you probably are already aware, if n is composite, i.e. a product of two things with neither of them being 1 or n, then we're not a field. And probably the easiest way to see that is, well, just running through the axioms, it's going to satisfy pretty much all of those axioms, right? With the exception of two things. You sort of start seeing quite quickly where the issue is going to be, and that's going to be the existence of inverses. And, yeah, well, the existence of inverses. Existence of 1 is fine. It's still got a 1, something that you multiply on and you get 1. So the 1's not the problem. It's existence of inverses. So to see this, first of all, if you wanted to work it out yourself, you work in some small examples, Z6 or something first, or Z4. But let's just go straight to Zn. So the point is that if, well, maybe I need to add a line. If, let's take a non-zero element A. Let's take A, which is non-zero. well, I just make it not 0. Well, sorry. Maybe I want to just write it like this. Note that A is not 0 in Zn. So it's the A from up above. I mean, it's not 0 because A is something strictly between 1 and n. Okay, so it's one of the non-zero elements in Zn. If A is invertible, so i.e. if we've got a field, then this equation, now I'm continuing what I wrote earlier, we've got the equation AB equals n in Z. It's often a bit confusing when you've got equations in Z and Zn, so I'll clarify that by putting little brackets or something. So that tells us that A times B equals 0 in Zn. So if there was an inverse, then I multiply by that inverse. And really, I'm using some axioms here to group things together. So that would be by, well, let's just keep going. Okay, so the idea is as soon as we've got that factorization of n as a product of two things, neither A nor B can be invertible. Okay. But maybe you should just think in Z6. So for example, in Z6, 2 doesn't have an inverse because we just start multiplying 2 by 1, 2, 3, 4, 5. None of them are 1 in Z6. Okay. All right. We'll go for just a few more minutes before we have a break. Any questions? You might notice that in this calculation I did something between here and here, which wasn't actually an axiom. Wasn't quite an axiom. We're going to actually prove that 0 times anything is actually 0 in a few minutes, but of course we're working in Zn here where we know how to do things, so we don't have to be too worried. Okay, so I'm not writing out in that working exactly which axioms I'm using because I'm not really doing it in an axiomatic way. I'm using it knowing what Zn is. I mean, it's a calculation in Zn which I know and love. All right. I'll come back to what I was just saying in a minute. So if P is prime, then Zp actually is a field. And if you run through those axioms in your mind with the associativity, distributivity, all that, commutativity, all that stuff, it's clear that everything holds, again, except the one thing that's definitely not clear is the existence of inverses. And there's lots and lots of different ways of proving the existence of inverses in Zp. All of them are a little bit clever or use something. So in essence, it's not a completely trivial fact. It's not an obvious fact. So there's various strategies. One way is to use Bezout's identity. That's what I'll go for here. So Bezout's identity says that you've probably done the Euclidean division algorithm at some stage. And when you read off all of your P's and Q's and R's or whatever, when you do the Euclidean division, it tells you how to write the greatest common divisor as a linear combination of the A and the B that you started with. Maybe you remember that. I'll put it in a tutorial anyway if you don't. Let me just write it down, what it is. So Bezout's identity tells you, and it's a consequence of the Euclidean algorithm, is that if the greatest common divisor of A and B is D, then, this is just in the integers, then there are integers lambda and mu such that lambda A plus mu B equals D. Okay, good. So it's, as I say, consequence of Euclidean algorithm, and Euclidean algorithm even tells you how to find lambda and mu. So now continuing with the proof that we've got a field. So if A and B, if A, oops, just A now. If A is in ZP but not 0, then now this is the place where we'll use that we've got a prime. The greatest common divisor of A and P has to be 1. Okay, so that's what would go wrong if we're not a field. If we're not a prime. Okay. And so by Bazoo, in Z. Now the B that I'm using here is P, so it's P. That's an equation in Z. As I say, working in ZP or Zn, it's often this blurriness. You do some stuff in Z and then reduce it down mod N or mod P in this case to something in ZP. So now we do that reduction. If I make this an equation in ZP, well, P is 0 in ZP. So now lambda, or more precisely lambda, because lambda was an integer, more precisely lambda mod P, I mean the P reduction of lambda, is an inverse of A. Oh, whoops, so I'll just write lambda though. So lambda is an inverse of A. I'll just write it as lambda equals A inverse. All right, so I had to use something. It's not super deep, because Bazoo's identity is not like an ultra-deep theorem, but it's a non-trivial statement. So, any questions about that? So far we've just got the 3 examples at this stage. We'll see some more in a few minutes. We've got the rational numbers, the real numbers, the complex numbers, and ZP with P prime. And there's a clear distinction between the first 3 and the last one. There's infinite fields and there's finite fields. We'll come back and discuss that in a minute. Just a little remark here. When you're working in any field, you can sort of imagine n like the integer 100. You can imagine what 100 is in the field, but it has a meaning. It has a specific meaning as you take the identity of the field. I've already said the identity. We're going to prove it's unique in a few minutes. But you take the 1 of the field and start adding it to itself n times, and that's what you can call that n in the field. So for example, in Z5, 10 means 1 plus 1 plus 1 plus 1 10 times, which is good. That's 0, as we expected. But that's what 10... So in any field, you can always think of... I mean, the n that you get won't be the integer, but you sort of imagine 1 plus 1 plus 1 n times. Does that make sense? So, anyway, it's just a notational thing. Sometimes you write integer... Well, it's not that the integer's in the field, it's that that symbol n is given that meaning. I think that's a good place to have a 5-minute break. Does anyone have questions? Well, feel free to talk amongst yourselves, stretch your legs. Don't get too loud, but talk as you like. Right. Okay, yep. Yep.
In first year, now I'm in third year. So in second year, I did mathematics.
Okay.
Along with my other to do SW.
Okay.
So I might find on something, I'm not sure.
Yeah, so, yeah. So I think the best thing to do... Since you haven't turned that off, I think...
None of it was really good. And I was like, oh, it doesn't matter. So it's the same thing. It's like watching
Actually, I don't think we have this one. Good.
I've proven it before. Around about I
What do you mean by around that?
But so we can read it with a prime. If you take it modulo y, I'll figure it out. I don't know what to do with the argument, but there's no sort of picture of actually, I should
Yeah, sure.
I'm excited to be the recipient.
All right, good. Maybe we'll power on. Any questions after having a bit of a think? All right. Okay. Okay, so let's just carry on with fields. Yeah, so just to try to emphasize it, it's at a certain point, like well after today basically, unless you're really explicitly asked, prove this statement about a field, proving the axioms of fields, that's when you have to do everything very carefully, like what we're about to do. But in reality, you will start getting more comfortable working with fields, just like we do with the reals, complexes, rationals, and just manipulate symbols much more like we do in those special cases, without being such a stickler for all the details. So the point, but this is really the one lemma, I think, where we're going to be super pedantic about using the field axioms to prove some other basic properties of fields which follow from those axioms. So somehow, I mean, you could have thrown these things in as additional axioms, but that wouldn't have been so wise because they actually follow from the axioms we already had. And the point of this lemma, as you start looking through it and digesting while I'm speaking what those things are actually saying, they're all saying extremely obvious things that if those things weren't true in a field, we'd be rather worried. Okay, so it's really this lemma is telling us all of the things we know and love in a field the way we expect with the reals and the complexes and stuff. To a large extent, all of those things remain true in general. So the first one is that the zero, because in a field axioms there was R0 and R1, but they weren't the 0 and the 1, but they actually are the 0 and the 1. They're unique. And also additive inverses are unique. So for each field element, the thing which was, a thing which is called the additive inverse, there's exactly one of them. Similarly with inverses, multiplicative inverses, lambda inverse. Another property that's very useful in a field is if lambda times mu equals 0, then either lambda is 0 or mu is 0. That's a good way to see that Z6 is not a field now, because in Z6, 2 times 3 equals 0, but neither 2 nor 3 are 0. So that would have sped up our proof, I guess. But the proof we did in Zn, that's how you prove this. Anyway, if also solving equations, so to speak, if lambda plus mu equals mu, then lambda is 0. That's what you hope. Here's a nice one that says that, but to digest what this actually is saying, this is saying that the additive inverse of 1 multiplied by a lambda equals the additive inverse of lambda. So it's like there's two different things going on, but luckily they're the same, so we can start blurring the distinction between those two things. And similarly, this last one, this is sort of what I used earlier in Zn without much comment, but 0 times anything is 0. So just already to say, if you understood how that Zn being not a field proof went, that's how you would prove this. However, we did use that A inverse times 0 was 0, so we're using this one down here. So you better prove that first. So if I wanted to repeat my proof of Zn not being a field in this general context, I would first prove this, and then I'd come up and prove that exactly the same way as I did earlier. Anyway, I'm just going to work through some of these, in fact, one of them, and the rest I'm going to leave as enjoyable exercises. All right, so let's just do 1. Let's look at what 1 is. 1 is saying that the 0 and the 1 are unique. So let's say we've got 2 zeros. So both satisfy the 0 plus lambda equals lambda. So the condition of being a 0. For all lambda in F. Remember that upside down A just means for all, in case you've forgotten. All right, so then the point of how you show something's unique, you show that you suppose there's 2 of them and show that they have to be the same. So it's a bit of just pushing stuff around, but in this lemma, this is where we're going to say very, very precisely which field axioms we're using. So we're going to use the fact that 0 is a 0. So I'm going to use this, I'm going to use A with a particular lambda equaling 0 prime. So using A, that says that this is equal to, so that's, the 0 prime is actually the right-hand side of equation A up there. So then I'll get 0 plus 0 prime. But then I want to use B, of course, but B, the way it's technically set up, you know, I need to swap the order of the summation there, but that's fine because everything's commutative. And then that's now set up exactly to be equation B with lambda equals 0. So that's 0. So you say, and there's all kinds of different, I mean, I've done it a fairly efficient way, but there's quicker ways, or not quick, I mean, that's probably the quickest way, but there's other ways of going around using the axioms and you get to the final answer, that's fine by one way or the other. But you see, the point is of this little, and it's really isolated to this lemma or questions where it says using the field axioms prove blah, blah, blah. Where just every single equality that we encounter along the way needs to be associated with an axiom that we're using. Okay? There shouldn't be any equalities that don't tell us how we got from that equality to the other, from one side of the equality to the other. We should say which axiom we're using. And you should only be using one axiom at each step. However, admittedly, when you come to, so the tutorial has the full, you'll work out all of these in the tutorial and it'll have full solutions, but there's definitely some efficiency, as I say, once we prove this one using the axioms in the proof of this lemma, then we can use it when we're proving this one, for example, so we don't have to do it in the order said, and that's probably how I'll do it in the tutorial. That's how I'm sure my solutions, the solutions will be written out. Anyway, all right, and so I've only done it for 0. The argument for 1 is simple, is similar. See, shoot, or do it as an exercise for the rest. Okay. Now, point, I just make sure you understand the point of this lemma. It's just that all the nice things happen that you want, and you have to, once in your life, prove them directly from the axioms to check. Okay. And then after that point, unless you're explicitly asked to prove it using the axioms, freely use all of those properties. Okay. All right. And that's the point, that the usual algebraic manipulations can be done in any field. Now, once we've got a field, it's often convenient to be able to talk about subfields of a field. Sub everything in mathematics is kind of useful. Like once you've got a vector space, you look at subspaces. When you've got a group, you look at subgroups, all kinds of stuff like this. So in terms of fields, of course, we've already got some examples of that. We've got that R is a subfield of the complex numbers. Q, in turn, is a subfield of the real numbers. ZP is not going to be a subfield of the real numbers. And the reason there is because to be a subfield, part of that's going to be requiring that the operations are the same in the two. You've got a field and some subset, and with the same, so to define a subfield in loose terms, or in fairly precise terms, in fact, a subfield should just be a subset, which is a field itself with the operations that it's inheriting from the larger set. Okay. So ZP, yeah, it's a field, but that's with a different set of operations than the ones that we would have done if we were working in the real numbers. Okay. So that's it. So subfield definition, a subfield is just simply a subset that is itself a field with the inherited operations. That's important. And the point is, okay, so to check something's a field, you in principle have to check all 9 of these axioms, and it's unlikely I'm going to get you to check all 9 axioms in any given example, but in principle that's what you have to do. But because if you have a subset using the same operations, well, the addition is certainly already going to be commutative because it's the same addition as up above, up in the bigger set. Multiplication is already going to be commutative. Associativity is automatically going to hold. Distributivity is automatically going to hold. The only things that could go wrong are really essentially the closure properties, that when I try to add 2 things in my subset, I might escape the subset. And then that's not going to be a field with the inherited operations. Because part of being a field, there were sort of those axioms that were a little bit hidden. Part of being a field is that when you've got a lambda and a mu, then lambda plus mu and lambda times mu are both elements of the field. Okay, so essentially subfield, it's going to boil down to simply being closed under respective things, and those respective things are going to be addition, multiplication, but also inversion is going to be important. And to have inversion, we better have the 1 in there as well. All right, but the point is, as I've said, is that because you're a field, F is already a field, you don't have to check a million axioms, you just have to check a few smaller ones. And again, it's, yes, you should remember this, but it's more for your mentally making a quick decision, is something a subfield or not. You're essentially just checking the main ones I said earlier is the closure, and we better check closure under the 2 inversion operations, additive and inverse. And really, this is a bit more of something, if you leave this out, you'll get things you don't want to be a field. A field's meant to have a 1, so to be if F prime is any hope to be a field, it had better have the identity in it as well. The 0 is going to be forced, because why is the 0 already there? Because if because I can take 1. First of all, it's already hidden in here that my subset has to be non-empty because I've said it has to contain 1. And then once I've got 1, I'm meant to have -1 as well, the additive inverse of 1. And then once I've got -1, by the closure here, I've got 1 plus -1, which is 0. So I'm forced to have 0 in there. So basically what I'm going through in those words, I'm not going to write out the proof, but now I want you to look back at all 9 axioms of a field and just check, do they all hold? Well, maybe we just do it quickly in our heads. The first one was associativity. Yes, because it's the inherited operation. So those ones just about the operation, they're inherited. There's nothing to do. Associativity, yes. Commutativity, yes. So that's F1, F2, F3, F4, I think, the way we numbered it. F5 and F6 were the existence of 0 and the existence of 1. We just proved the existence of 0. It did require an argument, and let's go through that again. You've got 1 in there, so you've got -1 in there, so you've got 0 in there. Okay. It's got 1. That's actually one of the things we've just stipulated here. And then the existence of additive inverses and multiplicative inverses. That was F7 and 8. I mean, I happen to remember the numbering just because we went through them, but I'll forget it by tomorrow. F7 and F8, but that's exactly what we're saying here and here. And then F9, that was about distributivity, but that again, that's purely about the operations, and the operations are inherited, so that holds. So there's nothing to prove. You have to prove that one thing, actually, that 0 lies in there. All right. I sort of say this one, there's something later called subspace criteria for vector spaces, which we use even more, but it's just some beefed up version of this. All right. So let's look at an example. Finally get a new field that we haven't already seen, because I suspect, well, I know you've already seen the reals, the rationals, the complex numbers, and you've also seen ZP. I should have said earlier, of course, like Z itself, the integers, that's of course not a field, right? Because it doesn't have inverses. 2 inverse, which is a half, is not in Z. But let's finally see a new field, maybe new. So this notation Q round brackets root 2, this means the field Q adjoined the element root 2. That's how you say it. But how it's defined is just on the right-hand side there. It's the set of all elements which are linear combinations of 1 and root 2. In other words, everything it's A plus B times root 2, or root 2 times B. Where the coefficients, the A and the B there, are rational numbers. Okay. So it's certainly a subset of the real numbers, or it's a subset of C, that's fine. Okay, so let's work C for why not. So it's a subset of C, and we want to just check that it's a subfield, so we want to quickly check the subfield criteria. Well, good, 1 is already in there, that's fine. Closure, oh, sorry, this was, yeah, closure. This is also obvious, but we better check that. When you add two things of this form, it's clear you get something of that form, just by grouping terms together. Maybe when you multiply, we'd better check that. So when we multiply here, well, I've done the calculation. You've got to use, of course, at some stage, root 2 times root 2 equals 2. That's where that guy comes from. And then we get a rational number plus root 2 times a rational number. So it's of the right form. So it's closed under the operations. Has to be closed under the inversion and additive inverses. Additive inverses, or negatives, that's the same thing. Inverses is clear because A plus root 2B, its additive inverse is minus A plus minus B times root 2. That's clearly still in there because it's of the prescribed form. And the one thing to check actually is that it's closed under inversion. That's the non-trivial bit there. So let's do that. And you do that by first working in the real numbers or the complex numbers. Maybe I don't know why I said C there. I preferred it. Let's work in our bigger field. In this like more natural, smaller field there are. Plus root 2b, or b root 2, how we've written it up above. The reason that's not clearly in our set Q adjoin root 2 because it's not written as a rational number plus another rational number times root 2. So I have to do that, and you probably know what to do. What should I do? Yeah, rationalise the denominator. And you multiply that out. And that equals what you want. So in particular, we've succeeded in explicitly writing it as one rational number plus another rational number times root 2. Okay. Somewhere along the way, we did something. We did this little trick here. And we better actually check that we didn't do something stupid there. And there's something stupid that people might often do without just symbolically is divide by 0. I mean, if a minus b root 2 was 0, you'd be in trouble. Okay, but of course it's not, because that would say root 2 is b on a or a on b or something, which is rational. So there, I've got that down there. So note we needed a minus b root 2 to not be 0, but if it was 0, then we're rational, which is ridiculous. So the point is, I mean, if I tried to take combinations of things a plus 2b without root 2, and I tried to define operations and tried to do such a thing, I mean, I get in trouble, of course, because I could be dividing by 0. All right, so that's a nice field. That's the simplest version of an algebraic, what's called an algebraic number field. And we'll discuss a bit more about that soon. Now I've got a question which looks simple at the beginning, that then when you start unpacking it, I mean, it is simple, so to speak, that you can do this without needing too much, but you really will have to actually think through this, I suspect. So let's try to do the same thing with the root 2 replaced by the cube root of 2. And let's ask, is that a field? And, well, okay, I've already said a hint, is it closed under multiplication? The answer is no, it's not going to be, but it's also not going to be closed under inversion as well, but even not under multiplication. And the point is, but I'll tell you this part, but you still have to prove this, what I say. That so, I mean, that element there is in this set, okay, because it's taking a to be 0 and b to be 1. So multiplying it by itself, so cube root of 2 squared, is meant to also be here. So what you have to now prove is that the cube root of 2 squared, so 2 to the 2/3, power of 2/3, is not expressible as a plus b times the cube root of 2. Okay, so you have to do some, it's a bit like, it's quite fun, these types of things, because you know, like it's a step up from showing that root 2 is irrational. To say root 2 is irrational is saying that root 2 can't be written as a over b. This is sort of something similar. It's saying that the cube root of 2 squared can't be written in terms of rational numbers and combinations of this other irrational number. Okay, so anyway, give that a go. You'll cube things and play around with symbols, push things around. You'll eventually get there. It's quite nice. And it'll be in a tube. All right, so the answer is no. But we're going to come back to that a little bit later. You can fix it up if you just add a third term, c, plus c times cube root of 2 squared. That thing is a field. Okay, but again, not immediately obvious. We'll come back to that. All right. So sorry, I know it's going kind of fast today because a lot of it's pre-prepared. Do ask me to slow down if anything. At any time. All right. Now there's a remark, and this is formally we're not really doing what's called ring and ring theory in this course, but it's helpful to have the name ring to use as an adjective for things that are not quite fields, basically. And sometimes, like the integers. I want to give that a name. What is that? I mean, it's a set, yes, but it's got more structure than that. The integers, you can add things together. It's all great, but you just can't take inverses. So something like that, and even sometimes with other things you can't do even a little bit more. Such structures are called a ring. And so I just want to define that just so I can use that word. We won't study rings like particularly abstractly in this course, but anyway, a ring, it's a bit less restrictive than being a field. So it's a set with, again, the two operations of addition and multiplication like a field was meant to have. But now we just don't insist on these three axioms. Everything else has to hold. So it has to have commutative addition we still insist on that, but we don't insist on commutative multiplication. The ring of integers, that does have commutative multiplication, that's good, but that's not insisted. We don't insist on that when we talk more generally about a ring. Okay. So for example, matrices, n by n matrices, with entries in the real numbers or something, it's got an addition, got a multiplication, but that multiplication is not commutative. Okay. But the addition is. So that's a ring. But anyway, there might not be a multiplicative identity, so there may not be a 1 in your ring. And, well, certainly once you don't have an identity, you might not have inverses. But anyway, you might not, even if you do have an identity, you don't insist on multiplicative inverses. So, when you start studying just rings in general, you take the axioms minus these three, and then you can start studying those rings generally, and then you can start adding extra conditions in and study the theory of the rings that have these extra properties. And those are rings that with F4 are called commutative rings, when the multiplication is commutative, like the integers. And rings that have an inverse, not an inverse, an identity, multiplicative identity, are called unital rings. So the integers would be a commutative unital ring. Okay. So it has everything except for F8 is the integers, the set of integers. Anyway, so I just want that word, I want to understand that word, ring. And of course, here's examples. All fields are, of course, rings. They're the best type of ring in a way, because they satisfy these three extra axioms. Z is, of course, a ring, but not a field. That one, it is commutative and unital. N by n matrices with entries in fact, entries in any field, but let's say in the real numbers. This guy is a ring with the usual matrix operations. This is not commutative, but it is unital. There is the identity matrix is in there. What about just the set of all even integers to Z? Okay, so we have to think through our field axioms, well, our ring axioms. So yeah, it satisfies all of those axioms that we insist. I mean, you have to double check that, but just look at the axioms and check. In particular, you add two even integers together, you get an even integer. That's going to be important. Multiply two even integers together, you get an even integer. So it's closed under all of that stuff. So this is a ring, but notice this time we're not a unital ring because 1 is not in there. Okay, so this one is commutative. But not unital. All right. And more generally, NZ. Just everything is divisible by n. That's commutative and non-unital or not unital. All right. So that's a ring. Oh, there's more. Sorry, make sure you've digested that. Matrices are a good way of taking some base object in mathematics and making it a more complex. I mean, you get a higher level object by looking at matrices over that object. So here, this didn't have to be the reals. It could have been any field, and then I could make the ring of matrices over that field. It didn't even need to be a field. It could have been an arbitrary ring, like the integers, and then I could look at matrices over those integers. It could have been itself the ring of matrices of 7 by 7 matrices, and I look at the ring of 12 by 12 matrices whose entries are 7 by 7 matrices. So I'm in this ring structure. You can make very complicated rings by simpler procedures on easier rings, by taking matrices over that ring, for example. That's kind of worth noting. Next one that's important and we'll use in examples quite a lot. Because even though we're not studying ring theory, these objects that I'm talking about here, like matrices and polynomials, they are important, and we'll be using those as examples. And we'll sort of see this even when you want to study fields themselves. You actually, if you want to study finite fields in particular, you really start studying rings first and then looking at what are called quotient rings, and they become fields. So you actually construct fields from the ring theory, which is not the way we're going to go in this course, but next year. All right, so polynomials. Now we've got a field, or maybe a ring, and we define, this is a definition here, f square brackets x. So I'm expecting you to remember this definition. This is polynomials with coefficients in f. And now what does that really mean? Let's do an example. It means what you sort of think it means. So we've got, in terms of, when I say this thing's meant to be a ring, so I want to have a multiplication and an addition. So what are those addition and multiplications? Well, the addition is just the straightforward one, of course. So these two things, if I add them together, that's 6 plus 4x plus x squared. But that equals, I'm meant to be doing everything in Z5. So that's 1 plus 4x plus x squared. So as is common when we're working with Z5 or Zn, sometimes our intermediate steps are over our integer sort of numbers there, but at the end of the day we should write everything in terms of Z5. For the multiplication, of course, we just do what we would always do with polynomials. We expand together and group like terms. So the first one, we multiply the 2 onto everything, so that's 8 plus 6x plus 2x squared, and then we've got some more stuff, that's 4x plus 3x squared plus x cubed, and then group everything together. So that's 8, which is 3, plus 10x plus 5x squared plus x cubed. But then we're really working over, got too many lines, we're working over Z5, so that's 3 plus x cubed. Does that make sense?
So the 8 went to the 3.
Yep, 8 went to 3 because we're in Z5. 8, when I divide by 3, has remainder.
But was the 6x and the 4x, that stayed 10?
That's just because I actually did that addition in Z. The little bits in between are a mix of Z and Z5s. Nothing is wrong because 10 does mean what it means, what I said earlier in Z5. It means 1 plus 1 plus 1 plus 10 times. But that happens to be 0. But so at this step, yeah, I took the 6 and the 4 and I did the addition just still in my brain in Z, in fact. I probably would have been smarter to turn that to a 1 straight away. And 1 plus 4 is 5, which is 0. But anyway, basically what I'm saying is the intermediate steps might look different. The final step should be written all in terms of Z5.
They all mean like the same thing.
Exactly, yeah, they all mean the same thing. There's lots of ways of writing 0 in Z5 in a way. I could write it as 0, 5, 10, 15, minus 5, minus 10, and so on. But sort of strictly speaking, Z5 is meant to be the set 0, 1, 2, 3, 4. And at the end of the day, I should write everything back in terms of those 5 elements, 0, 1, 2, 3, 4. So, and that's what I've done with my coefficients, with my x's as well, of course. Yep.
And if you had x to the 6, that would stay x to the 6, or would it go?
Yep, good. Yes, good point. X to the power of 5, let's say, is just x to the power of 5. That exponent 5 doesn't get screwed around by the ZP-ness, the Z5. Okay, so x to the 5 is just x to the 5. X to the 6 is just x to the 6. It's only the coefficients where the operations are being done mod p in ZP. To say that another way, this is just, let me just rephrase, this ring of polynomials with coefficients in f, it's combinations of things where linear combinations of 1, x squared, x cubed, up to, you stop at some point, x to the 100 or something, like that would be a polynomial of degree 100. The coefficients are all in the field, and then you do the expansion, the product and the addition, the way you normally would with polynomials except the operations you do on the coefficients are done using the field operations, the operations of F. Yeah?
So I suppose we don't need to define multiplication in the usual sense. We define it as being a composite, like taking composition of functions. We also define multiplication like
Sort of, but be careful, it's not composition of polynomials here, because multiplication of two polynomials is certainly not composing the two polynomials.
we could also do that, and I suppose if that satisfies the conditions.
You could indeed. The problem, okay, if you took composition, it's not going to satisfy the conditions of the field.
Oh, it's going to satisfy perhaps rings or not.
Yeah, could satisfy rings. That's right. Yeah.
In Euler's theorem, would there be a maximum order to
No. So these polynomials are allowed to go. What do you mean by the order of the polynomial? First of all, in fact.
for Euler's theorem? The largest power that you have of x before it comes to
Good. So in ZP itself, or in any finite field, when you start taking an element and start raising it to higher and higher powers, eventually you'll get back to the identity. But that's not happening in this ring here. This is still a ring of what's called characteristic 5, meaning 1 plus 1 plus 1 is 0. So there's a light right in my face. But when you take just the polynomial x here and you square it, it goes to x squared. And then raise it to the third power to x cubed. And all of these are distinct elements in this polynomial ring. So the difference here is the polynomial ring that we're talking about here is not, even though Z5 is finite, this is not finite. So Euler's theorem, you need your group, let's say, or whatever we're talking about, has to be a finite group, and this isn't. Coefficients live in a finite field, but the set of polynomials is infinite. All of the elements 1, x squared, x cubed, and so on. In fact, this structure, this has the structure of a vector space over the field F, where the vectors, a basis, can be taken to be 1, x squared, x cubed, x third, no, x fourth, whatever, all of the powers of x, and then everything is a linear combination. But all of those powers of x are all linearly independent. So this is, once we start talking about vector spaces, already tomorrow, this is an infinite dimensional vector space over the field F. Yeah?
So does that mean, like, when you're taking, like, equality between polynomials here, is it purely coefficient-wise?
Good, yeah.
Exactly.
In this ring of polynomials, to say polynomial A equals polynomial B means that the constant terms are the same, the coefficients of x are the same, the coefficients of x squared are the same. That's exactly what it means, just equality. Notice you can define this ring in a much more ugly-looking way, in a way. You can never put the x's are somehow these place markers which tell us how to do this, in particular, multiplication down here. And we're so familiar with how we expand out polynomials that that's helpful. But you could more abstractly define this. Just take a polynomial. What is a polynomial? It's just a sequence of coefficients. Forget the x's. Just write out a sequence of coefficients, a0, a1, a2, a3, ... with only finitely many non-zeros. So at some point they all become 0 to be a polynomial. And then take another polynomial as a sequence. It would be b0, b1, b2, b3, blah, blah, blah. And then define what it means for A, this first sequence, times B, this second sequence. This is a third sequence where the first term, I can do the first term, that's A0 times B0. The next term is going to be A0 times B1 plus A1 times B0. The next term would be A2 times B0 plus A2A1 B1 plus whatever. It's when you got to, but that's I get my brain stops there because I'm thinking, I'm trying to think of how do you multiply out polynomials. But it would be, how do you get a term of degree k? You multiply something of degree I with k minus I in the second polynomial. So you just think of all the ways of doing that. But notice that definition of multiplication would not be very transparent or nice to work with. So polynomials, it's amazing that it is so intuitive when you define it this way. All right. Good, so we'll definitely use that example. You'll study rings a lot more in 3962, but for now, I definitely want you to know the examples up above. Okay. And it's more, as I say, it's more that I just need to use the ring because I need that adjective. Otherwise, I say the set of polynomials or something. But I don't mean that. Saying ring, I mean with those operations as well. I mean, I'm giving more. Anyway, so to finish off today, we'll start talking about when two fields are the same. This happens all the time in all abstract mathematics. You want when are two things the same up to what you called the elements. So when are they basically, when are their structures, well, the word is isomorphic, but when are they, for all sensible purposes, the same? So a field, what's a field? A field's determined, it's all about its operations, so it's determined by its addition and multiplication tables, where, you know, you write out the elements of the field, possibly infinite, but let's imagine finite field, A's and B's, and then in the corresponding entry there you write A plus B. And similarly for multiplication, looks like there's a minus sign in the multiplication. I didn't mean that. Just get rid of that. So for example, in the field Z3, well, I can do this really quickly. This one. That's the addition and multiplication tables in the field Z3. Just a comment there. Yes, in the addition table we see every entry appearing once in here. You might like to think about why that's always true. And now two fields might be, well, we'd like to consider them as the same if their operation tables were the same, just up to what I called these elements. Like in Z3, yeah, I called these 0, 1 and 2, but I could have called it red, green and blue, and had a multiplication table with red, greens and blues. And from that, red would have to have been the 0, blue would have had to have been the 1, and, well, green was something else. Green would have been -1 or whatever. You can work it out in terms of the other ones. But, yeah, so you could make that multiplication table just with different names for the elements, but they're, of course, for, you know, abstractly, they're the same field. Even though they're not the same field, because one has elements 0, 1, 2, the other one has elements red, green, blue. But if I'm only caring about the field structure, they behave in exactly the same way. Make some sense? So two fields that have the same tables are called isomorphic. And let's just quickly make that a definition. So to talk about an isomorphism, we need the idea of a homomorphism first, and that's something we'll talk about in vector spaces again and with groups again. So homomorphism basically in mathematics, just to try to intuitively what it means, it's a map between certain structures, same types of structures, in this case fields, and it should preserve the operations of the field, of the whatever the structure was, in this case a field. So to say it preserves the structure when I have two fields means that when I take psi of a sum of things, I should get the sum of the size of the things. And multiplication similarly. But notice there's some subtlety here, right? That's the operation in F, and that one is the operation in F prime. They could be completely different things. I mean, one could be ZP and one could be the reals or something like that. I mean, you know, like in principle, you're allowing all kinds of different operations, but we're still writing them both as a plus. And it's up to us to realise from context, or, you know, because A and B live in F, so that's obviously the operation in F. Psi of A and psi of B both live in F prime, so that's obviously the operation in F prime. So that's a homomorphism is a map taking it from one to the other, which preserves the structure in that sense. And then if it preserves the structure really, really well, that's an isomorphism. So that means it should be bijective, so that everything over in F prime comes from an F, and moreover, two different things in F go to two different things in F prime, so you get no collapsing. So everything is seen in the image equals the codomain, and nothing is collapsed, being injective. Okay. And that's then called an isomorphism, and if two fields are isomorphic, well, if there exists an isomorphism, we say the fields are isomorphic. That same concept is going to come up at least 2 more times, as I say, with vector spaces. There's going to be 2 operations on a vector space. There's going to be adding 2 vectors and multiplying a vector by a scalar. And so a homomorphism is going to be something that preserves the addition of vectors in the, basically like number 1. And number 2 is going to be preserves the scalar multiplication. So it's going to be a bit different, that one, but we'll see it. Now, I mean, to actually give a non-obvious somehow example of an isomorphism, you know, this calling the elements of Z3 red, green, and blue, or whatever, is a bit stupid, of course. But here's a more natural one. So we've got our favourite, well, we've got our complex numbers, which we learned from school by sort of randomly, so to speak, taking the adding something I squared equals -1. But you don't really have to do that if you just work with matrices. Instead, you just take F to be this set of matrices, 2 by 2 matrices of this prescribed form, with A and B being in the real numbers. And it's just got the normal matrix operations. So as an exercise, I want you to check that it's a field. Okay? You actually have to check everything here, because it's not a subfield of some bigger thing. Well, it is subfields of things, but it's not subfield of any natural thing that we already know. So here, actually, I want you to look, maybe not write too much down, but look through the axioms and check them all. Important ones are going to be the 2 hidden axioms, in fact, the closure still. Adding 2 things of this form, you get something in this form, and harder to see by just eyeballing it. You have to do the multiplication. Multiplying 2 things of this form, you get something of this form. That's the key one. Checking inverses, that's going to be important. Anyway, so there's a bit to do there, so I recommend you actually do that. But remember the 2 hidden axioms, okay? The ones about operations. And then, okay, there's a map where I can send A plus IB to that matrix and check that this is an isomorphism. So what you have to do there, so I am going to leave it as an exercise, but the first thing you have to do is check that it satisfies that property up there. Those 2 properties. So I have to check, okay, A's and B's mean different things than what they did on that previous slide, but I have to check if I have an A plus IB and a C plus ID, then when I apply psi to A plus IB times C plus ID, I get psi of A plus IB times psi of C plus ID. I.e. that this matrix multiplication, well, the way matrix multiplication for these types of matrices works is exactly the same as the way complex number multiplication works. And similarly for addition. That's what it's saying more intuitively. And then you have to check it's an isomorphism. Well, it's clearly, so once you know it's a homomorphism, you'll have to do that. That's a bit of calculation, writing out matrix multiplication. To check it's an isomorphism, well, of course, 2 different things over here go to 2 different things, because, you know, if 2 of such matrices are the same, then their A's and their B's are the same, which means the reals and imaginary parts were the same, so you had the same complex number. And it's clearly surjective too by the definition that everything is of the form, the prescribed form. So once it's a homomorphism, it's obviously bijective. So that's an isomorphism. So what it says more intuitively now, instead of dealing with A plus IB, you could deal with these matrices and do all of complex number stuff with those. You don't want to do that because A plus IB is a more intuitive thing to work with once you get used to it. But anyway, it's a nice way you can talk about the complex numbers without ever inventing I. And you might like to check that just as a comment or something, you don't have to check it anywhere in this exercise, but there should be I still. I mean, I is the number 0, 1, -1, 0. That's the I squared equals -1. And you just do that matrix multiplication. It's minus the identity. So in the matrix land, there's no surprise that there's a matrix which squares to minus the identity. But when you're talking about complex numbers for the first time, that seems like blows your mind. Just a little exercise here. Homomorphisms, because they preserve the structure, and this is almost a tautology, this exercise, because they preserve the structure, they preserve the structure. So they map the 0 over here to the 0 over here, the 1 to the 1, negative, the additive inverse of lambda goes to the additive inverse of psi of lambda, and similarly with inverses. Okay? So again, that's just prove it from the definition of what a homomorphism, what an isomorphism is. And I see we're coming up to lecture 2, so I think that's a good place to stop, except for questions. So today's a little bit different. There's a lot more covered today than normal somehow, and a bit more discussion. But yep.
So for that example of complex numbers in the matrix, you check first that it's a homomorphism.
Yep.
And then you show that it's bijective.
Exactly. So all the time, whenever you're showing something as an isomorphism, first thing is always show it's a homomorphism, and then check injective and surjective. Good. Okay, I'll see you tomorrow, or whenever it is. Tomorrow.
Why bother teaching? You have isomorphism or group isomorphism. That's crazy. That's crazy. I am. Because of more simple structure, which better outline, more simple things that outline the context.